I am very, very early. Hello, everyone. Come on in. All both of you. How's everyone doing? Anybody have any questions before we get started?
Nope, I'm all right.
Good deal. Yeah, Jack and Nathan's here. I'm assuming some more people will come in. What I want to do is I want to work at, at least a couple ideal gas law equations or problems, just because we covered the ideal gas law, and I know you've all had chemistry, or I think I asked everybody that they had chemistry. Most people who are in calculus-based physics have had at least chemistry in high school. If you haven't, though, make sure you ask me for help if you have any difficulties on applying it. Some rules that you got to remember, though. Sometimes you'll do an ideal gas law equation or a problem where they're talking about a gas that's over top of water. So like if you've ever taken, a test tube with air in it and you stick it under the water, it almost fills up, you pull it out, it leaves a little near vacuum of air up top. Well, that's not quite a vacuum for starters, but the other thing is it's got a vapor pressure in there. So you have to take that vapor pressure into account if it's over water. And our book has a table of those vapor pressures for given temperatures. So you got to take that into account when you're using the ideal gas law in an over with the water situation. Okay. I don't recall seeing any in the homework that I assigned for this chapter 19, but just in case, I want you to know that's there. Another thing is we want to mention that there's another version of the ideal gas law, and that's what I'm going to start off with, showing you another version of the ideal gas law. And then I'm going to talk a little bit about the shortcomings of the ideal gas law, even though it's just very powerful and we can use it in a lot of results. In fact, Ralph Alpher, who was part of the alpha beta gamma paper that basically not only said the Big Bang was happening, but was wrote an article that suggested to look for a 2.7 Kelvin microwave background radiation. And sadly, the poor guy was hanging out to dry, I should say, or left to hang out to dry, because his PhD advisor, George Gamow, realized that he couldn't actually, write a paper with one guy's name Alpha and another guy's name Gamow that looks like alpha gamma without a beta. So he got Hans Beth, whose name looks like beta, of course, to be a co-author. And he was reluctant to do it, but he said the grad student was cool with it and they liked the idea. So they wrote this alpha beta gamma paper, but everybody thought it was Gamow playing a joke, so nobody read it. So sadly, that poor guy could have possibly gotten a Nobel Prize for his PhD thesis, and that's like, that never happens. But he did a lot of that work with just the ideal gas law, because right after the Big Bang, the temperatures are really high, the densities are really low. And that's exactly when the ideal gas law works best, at low densities and or high temperatures. So it's not as weak as you might think, but I'm going to give you basically the Clausius equation of state, which is just short of the van der Waals equation, and then I'll give you the van der Waals equation. So let's go ahead and get started. I will be posting, just for the record, I will be posting a test sometime this week. And that'll be on the next two chapters, because I don't think we've had a test since the midterm. So it'll be the next, at least 2, maybe 3, but I'll put up a practice test, and then I'll put up a next test, and I'll give you at least, 10 days, 7 days, something like that with the test and the practice test to do it. And then over the break, we're going to have that retest midterm, which I'll make available before you go on Thanksgiving break. And then it'll probably be due like the Wednesday after Thanksgiving break, just in case anybody's traveling. I want them to have plenty of time to do it, not while they're traveling or seeing family. But if they wanted to, I wanted to have it available too. So Christian just came in. So Christian, do you have any questions before I move on? I've got my chat. Oh, cool. He spoke. Okay. So I've got my chat window open too. So if y'all don't want to talk, you can certainly post something there. So let me get into my iPad. So now I'm sharing. So we've already learned about the ideal gas law, and the ideal gas law is basically PV, well, PV, sorry about that, equals nRT, where N is the number of moles of the gas. So if it's a pure gas, then they'll say like it's hydrogen. So a hydrogen gas, for instance, that has a molecular weight of 2 because hydrogen is naturally occurring in the diatomic state. So in the diatomic state, that means it's 2 atoms bonded together because hydrogen is just one electron short of being happy. So the 2 group up together. That makes their molecular weight 2 grams per mole. So if they're giving you a mass of hydrogen gas, then you just divide that by the 2 grams per mole, and that'll give you the number of moles. If they gave you the number of atoms, then you could just divide the number of atoms by the number Avogadro's number, and that would give you the number of moles. R is the ideal gas constant. And again, if you guys go into engineering, y'all might learn something entirely different. But we use mostly in physics 8.314 joules per mole Kelvin, but there are other values, and your book mentions ones like 0.0821, something like that. That's the one where you use liters and atmospheres. So you use liters for volume and atmospheres for pressure. Here we're using P in units of newtons per square meter, which is defined to be a Pascal. We're using V in units of meters cubed. And we're using T in Kelvin. Now, notice Kelvin, converting it back and forth between Kelvin and Celsius is not just a multiplicative conversion. You don't just multiply, some Kelvin temperature times some number to get the Celsius. You actually have to add something to it. Similarly, you don't multiply Celsius times some number to get Fahrenheit. That's why equations don't necessarily usually like a certain type of temperature, but they like the other type. So for instance, a lot of these equations, you have to use exactly the right equation or the right units for temperature. So in this case, if you actually put the Charles's law, Boyle's law, and Gay-Lussac law together, you ultimately get that PV over T equals a constant. And that's for basically any fixed number of moles or any fixed mass of gas. So you could use this, for instance, if you're talking about a car tire that doesn't have a leak, because that mass without a leak, that mass will not be changing. And therefore that number of atoms will not be changing and number of moles will not be changing. So what we're saying is if you fix the constant amount of mass of gas or a constant amount of moles of gas, then N is a constant and R is a constant. And you can see from the ideal gas law, PV over T is equal to NR. So that's why that works. But that also allows you a new way of using it where you can say P1 V1 over T1 is equal to P2 V2 over T2. And this is where you see if you had units, for instance, of atmospheres, you could put an atmosphere in here. And because the atmosphere is just something you multiply by to get pascals, for instance, 1 atmosphere is 1.01 times 10 to the 5th Pascal. So you can just multiply the atmospheres times 1.013 times 10 to the 5th Pascal, and that'll automatically get it into pascals. So you could put ATM in here, and that works just fine. Similarly, you could put pascals in the P mark, or you could put millimeters of mercury would actually work as well, because there's a conversion between that. You could put torr. All those things are multiplicative conversions, so they're easy. But in this one, you can't put that T in there because the conversion between Celsius and Kelvin is the temperature in Kelvin is equal to the temperature in Celsius minus 273.15. So you see, there's no way I can subtract 273.15 and do the same thing on the other fraction denominator and have that work out. So that's why this has always got to be in Kelvin. So one thing I wanted to do is show you how much volume a mole of gas takes up at STP. So that also allows me to reintroduce STP just in case you guys have forgotten. So how, or let me say, what is the volume? What is the volume of any ideal gas at STP? Now that STP means standard temperature and pressure. Okay, so I should make a question mark out of that. All right, so what we're going to do is we're going to say PV equals nRT. Actually, let me go ahead and write it in red, say the solution. So PV is equal to nRT. What we're wanting is V. So V is equal to N times R times T over P. So V is going to be equal to 1.00 moles times 8.314 joules per mole Kelvin times the standard pressure, by the way, is 1 atmosphere, which is 1.013 times 10 to the 5th Pascal. And the standard temperature is 0 Celsius, which is 273.15 Kelvin. So you can see clearly the moles are cancel out with the mole in the bottom, and the Kelvins cancel out with the Kelvin in the bottom. And now all I got to divide by is the Pascals, and that's 1.013 times 10 to the 5th Pascal. I suspect all y'all should have this memorized, but if you don't, make sure you put it on your equation sheet so you'll have it, because I'm not necessarily going to supply that on any kind of tests. Now, when we do that, it's going to come out, and notice I've got a joule up top because the mole and the Kelvin have canceled out with the moles and the Kelvin, but I do have a joule up top left, and then a Pascal left in the bottom. Well, Pascal is a Newton per square meter, and a joule is a Newton meter. So if you divide a Newton meter by a Newton per square meter, that becomes a Newton per meter times a square meter divided by Newton. So you're left basically with meters cubed. So that's good. That's what we want. That's what our volume is supposed to be. So 1 times 8.314 times 290, or excuse me, 273.15. 8.314. Yeah, I got all that right. And then I'm going to divide that by 1.013 e to the 5 Pascal. Why did it say that? Okay, for some reason it told me I got an error and I don't see any here. Oh, I see it now. 314 times 273.15 divided by 1.013 e to the 5th. And that gives me 2.242, if you want, 2.242 times 10 to the negative 2 cubic meters. Now, cubic meters is something that most people don't get very good with, so it's often better to think in terms of liters. What we do know, for instance, is a liter, 1 liter, is defined to be basically a 10 centimeter by 10 centimeter by 10 centimeter cube. So if you took a cube like this, and this side was 10 centimeters, and this side was 10 centimeters, and this side was 10 centimeters, then that would be a volume, V equals 1,000 cubic centimeters. So I'll write cubic centimeters by writing the centimeters with a cube on it. But that's also defined to be 1 liter. So we can take that 2.242, that 2.424 or 2.242, excuse me, times 10 to the -2 cubic meters. And I can multiply that to get rid of the meters. Actually, let me fix this. That's aggravating me already. And the one time I want an eraser, it won't give me one. So 2.242 times 10 to the 3rd meters. I know that, in fact, 1 meter down here is equal to 100 centimeters. But there's a meter times a meter times a meter, so I got to do that 3 times. So 100 times 100 times 100 gives you 1,000,000. And then I can say, well, wait a second. I also know that now that I've got it in cubic centimeters, I know that 1,000 cubic centimeters is equal to 1 liter. So what we're going to do is going to multiply by 1,000,000 and then divide by 1,000. That's the same thing as multiplying by 3. And you get, in fact, 20, or excuse me, by 10 to the 3rd. So you get 22.42 liters. So that is something that people use all the time in science books. They just assume everybody knows that, and they'll say the volume of 1 mole of gas at STP is 22.4 liters. Okay, so that's like a fact that everybody sort of assumes when you're in a science curriculum or engineering curriculum. So it's worthwhile seeing the calculation once and then also making sure you can remember it. So I would say probably commit that to memory, especially if you're going into material science or mechanical engineering or stuff like that. Chemistry, chemical engineering. All right. So any questions on that one? Now, remember, we know that basically air is a gas, but it's actually a mixture of gas. We know it's about 80% nitrogen and about 20% oxygen. In fact, it's closer to like 79 and 19.5 or something like that. But that last percent is like water vapor. Argon, I think, is the most prevalent, but you can also have water vapor. You can have a bunch of different things. Obviously, there's carbon dioxide in it and all that good stuff. But the vast majority of it is nitrogen and oxygen. And what you have to realize is when they say that percentage, that's a percent by mass, not a percent by number of atoms. So if you wanted to know, for instance, what is the molecular weight of air, it's sort of wrong to even call it a molecular weight, but we'll say M air is equal to, what you do is you say 0.80 of the mass, that's 80%, and that should be nitrogen, which nitrogen is another diatomic molecule, and it's 14.0 and some change, but I'm just going to say 14.0 because that's close enough. Whoa. 14.0 grams per mole times 2, because it appears as diatomic, plus 0.20 times 16.0 grams per mole times 2 again. And then, of course, this is a weighted average, so you're supposed to then divide it by 0.8 plus 0.2. Well, 0.8 plus 0.2 is just 1, so we don't have to actually do that part. But when I calculate this, I think I got 28.8, so let's double check that. So 2 times 14 times 0.8, that gives me 22.4. And then 2 times 16 times 0.2, that gives me 6.4. And I add that to 22.4, and that gives me 28.8 grams per mole. So that's actually how you're supposed to reconnoiter, if you will, a molecular weight for air because of its mixed composition. I don't like how this unit turned out, so I'm making it better. So any questions on that? All right, so let's look at another one. Let's say we have a 8-inch radius balloon. A balloon that's supposed to be 2 O's has a 8.00 inch radius, approximately a sphere, and is filled with air at 2.00 atmospheres and 20.0 degrees Celsius. Okay. So what is the volume? I really don't have to ask you this question, but you have to calculate it. So I figured I'd go ahead and do that. What is the volume of the balloon and then B, how many moles, I just started writing lowercase for some reason, does it hold? Okay, so let's do part A first. So volume for a sphere is 4/3 pi r cubed, and our r is 8 inches. And of course, 1 inch is 2.54 centimeters. And then of course, 100 centimeters is equal to 1 meter. Okay. So 8 times 2.54, 8 times 2 gives me 16, 18, 8 times 0.5 gives me 4. So that brings me up to 20. So that's 20.32. And then I divide that by 100, be 0.2032 meters. Okay. So now I can say the volume is 4/3 times pi times 0.2032 meters cubed, which is good because that's where we're going to get our units of cubic meters from. So I probably wouldn't hurt to check that arithmetic I did in my head. So 8 times 2.54 divided by 100 is 0.2032. So yeah, I got that right. Good deal. Cubed. And now I'm going to say times 3.14159 times 1.33333, and just put a bunch of threes in there. And that gives me a volume of 0.03515, carrying 1 extra sig fig. Okay. So that's the volume. And that was the answer to part A. And really, I didn't have to ask for that. Like I said, really, you just had to compute that to get the second answer. So I don't know why I just wrote an A there. So I'll write a B here. Now for part B, they want to know how many moles. Well, the ideal gas law says PV equals nRT. So that implies that N is going to be equal to PV over RT. So N is going to be the pressure, which is 2 atmospheres. But 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. And then the volume is 0.03515 cubic meters. And then the R is 8.314 joules per mole Kelvin times, now the temperature is 20 degrees Celsius, so that's 293.15 Kelvin. Okay. So when I do all this, I'm going to say that 0.035 times 2 times 1.013 e to the fifth. And now I'm going to divide that by, in parentheses, 8.314 times 293.15, close parentheses. And this gives me 2.921 moles. Okay. So that's how many moles you have of this gas. So that tells you basically you can figure out what the mass is like this, because we just computed that the molecular weight of air is equal to, and I'll put quotations around it, it's equal to 28.8 grams per mole. So it turns out that if we take and multiply 2.921 times 28.8, that'll give me grams. So I've got the actual mass of the air in the balloon is 84.14 grams, or 0.08414 kilograms. Again, carrying that extra sig fig. That wasn't asked for, but I just wanted you to see, in case you hadn't remembered from chemistry in high school how to do that and all that good stuff. And also gave us a chance to use that newly computed molecular weight. So 80% of that mass, let me see. So 67.31 grams of it is nitrogen. And then the rest is approximately oxygen. Again, I'm throwing away basically 1% of the material, but and that means about 16.83 grams of it is O2. Okay. So again, that just shows you how you can use that 0.8 and that 0.2. Any questions on that? So let's try another problem. Assuming we pull that balloon underwater very quickly, I just ran right into my U. Very quickly. What would its volume be at 33 feet of salt water, where let's do 66 feet. Where P has to equal 3 atmospheres. Okay. In other words, it's got two atmospheres of pressure. I'm going to bring it underwater, and then that water is going to force that to become basically 3 atmospheres of pressure. And I'm doing it quickly so that the air won't have enough time to change its temperature. It's going to have the same temperature it had. It's a sealed container, so it'll have the same number of moles it had. So really all that's happening here is pressure and volume are changing. So I can take that part of P1 V1 over T1 equals P2 V2 over T2. I can take just the P1 V1 equals P2 V2 part. Okay. Anybody have any questions on what I'm doing with that?
Yeah, if you did it quickly, wouldn't the temperature change immediately?
It would change really fast, but I'm just trying to take that out. We could do another problem and say the pressure and temperature is going to change, but I have to give another variable. So I can say it went from, say, 20 degrees Celsius to, let's say, 10 degrees Celsius. And then I'd have to use P1 V1 over T1 equals P2 V2 over T2.
If you did it infinitely slowly, wouldn't it allow for the temperature to dissipate?
I think if you did it infinitely slowly, it would definitely allow the air to reach equilibrium with the water around it. Whereas if you pull it quickly, that latex cover of the balloon is somewhat of an insulator, and it's pretty much going to keep it there. Now, because it's going to be compressed, that's actually going to increase the temperature all by itself anyways. But what we're trying to do is bring it down so rapidly that the water can't change its temperature. It's definitely going to have to change temperature just from the fact of being compressed. Remember, expansion of a gas actually causes it to cool, and compression of a gas actually causes it to heat up. So we're trying to avoid both of that just by doing it quickly.
Right. What I'm saying is if you just waited, it'll equalize on its own. If you did it impossibly slowly, then the temperature would just equalize on its own.
Yeah, but it would be a different temperature though. That's the only thing. It would reach equilibrium with the water temperature unless the water had the exact same temperature as the air did. So if the water was 20 degrees Celsius, which is like 84, and the air was 84 degrees Celsius, then yeah, infinitely slowly would be better. Does that make sense?
Yes.
Gotcha. All right. So with this in mind, all we know is we had 2.00 atmospheres times a volume of 0.03515, I think, 3515 cubic meters. And then afterwards, it's going to be 3.00 atmospheres. I'm trying to remember my old scuba diving facts, but if I remember correctly, it's at 33, 66, 99, and 129 feet that you increase by 1 atmosphere each step. So at the ocean's level, at sea level, you got 0 atmospheres or excuse me, 1 atmosphere because it's the air pressure. And then at 33 feet, you've got 2 atmospheres because it's 1 from the water and 1 from the air, and then 3 atmospheres at 66, and then 4 atmospheres at 99, and 5 atmospheres at 129. And that's also why when you get to that last 33 feet, you should take your slowest, make your descent the slowest at that one, because you're literally cutting your pressure in half by going up one. Whereas from going from 3 to 2, you're only cutting it by a third, and going from 4 to 5, excuse me, from 5 to 4, you're only cutting it by 0.2. So, all right, so that's going to be equal to V2 over here. So we can say V2 is actually going to be equal to 2.00 atmospheres over 3.00 atmospheres times 0.03515. Again, that's 1 extra sig fig cubic meters. So what you see is it's going to be V2 is going to equal 2/3 V1. That's an important figure. But calculating that, I just have to take this and multiply it by 2.03515 times 2 divided by 3 gives me 0.02343 cubic meters. So that was another way of me showing you, hey, basically, here's both ways you can use the ideal gas law. You can use it as PV over T, or PV times equals PV, or you can use PV equals nRT. So I just wanted to show you an example like that. Now, if we actually did what what Nathan and I were talking about, we could say, let's let this be part B. If the balloon reached equilibrium, temperature equilibrium, with the water T equals 10.0 degrees Celsius, what will be the new volume? So in that case, we're going to use solution P1 V1 over T1 is equal to P1 2 V2 over T2. So for that, we could say, all right, V2 is going to be equal to P1 V1 over T1 times T2 over P2. So when I write that, I'm going to get 2.0. I'm going to leave off the units this time, but 2.00 atmospheres times 0.03515 times T2, which is 10 degrees Celsius. So the new temperature is 10 degrees Celsius. So that's 283. And then the old temperature, of course, is 293.15. And the new pressure is 3.00 atmospheres. And you can see the atmospheres cancel out with the atmospheres, the kelvins cancel out with the kelvins, and all you're left with is volume. So really what I'm going to get is, I'm going to write it in somewhat of a symbolic form by taking 2 times 283.15. And then I'm going to divide that by parentheses 293.15 times 3, close parentheses. So in other words, I'm leaving off the volume right now just to get a pure number times the original volume. So now it's going to be 0.6439 times V1, which is equal to 0.03515. That gives me 0.02263. Oops. Cubic meters. So that's a third problem we can get from doing our ideal gas law. Any questions on that? Have any of you not had chemistry? You can answer in the chat if you want to. So it looks like everybody's had chemistry, so good. Okay, I always go kind of light on the ideal gas law problem specifically because almost everybody's already had it, at least in high school. But I feel bad even when I go light, which this is actually a little less than going light, but it is still somewhat light. So what I want to do now is I want to show you another version of the ideal gas law. What we do is we take PV equals nRT. And can someone tell me how you could calculate the number of moles if you knew, say, the number of atoms?
It's divided by Avogadro's number.
Exactly. So if you take the total number of atoms or molecules and divide it by Avogadro's number, and those of you that might have forgotten Avogadro's number, it's 6.022 times 10 to the 23rd. And that's reciprocal moles, because it's like atoms per mole or electrons per mole or grasshoppers per mole or whatever. So if I put that in here, now I've got PV equals N times R over NA times T. But it turns out that R over NA is actually defined to be the Boltzmann constant. And that's 1.3806 times 10 to the negative 23 joules per Kelvin. Okay, so an ideal gas law is this, but an ideal gas law is also PV equals N times KB times T. That's going to come in handy for the next thing I do, or the next thing I do. Any questions on that? Have y'all seen that before? Hopefully. Okay. All right. So what I want to tell you is, as I told you, the ideal gas law works for a lot of situations, but when you get high density gases, then that means there's a lot more atoms per cubic meter. And if there's a lot more atoms per cubic meter, that means the atoms are closer together, and you're more likely to get, say, some polarization of the individual atoms or molecules that'll cause them to attract. It also cuts down on the total volume you have. So if you try to take those things into account, you can get another version or two other versions. So for instance, if you want to try to take into account the volume issue, what you can do is you can say P times V minus the number of moles times B, where B is the lost volume per mole. In other words, if you knew the volume of whatever atom you're using, maybe you decide that you're losing due to it and due to its jiggling. Maybe you're deciding it's going to be twice the volume of an atom if you wanted to. So you calculate the volume of the atom, multiply it by 2, and then multiply it by Avogadro's number, and that would give you the B. Okay. So you'd put that B in there, and then you multiply that by the number of moles. And then this could all be said to be equal to nRT. So that's one way, and that's what they call the Clausius equation of state. So that's a closer approximation of reality. And it just shows that you don't have full access to the entire volume of the container, because you've got to steal some of that volume by having the atoms take up space, or having the molecules take up space. Okay. Now, the next step is you also want to say, well, when an actual gas is inside of a container, as the gas tries to get near the wall of the container, it's going to actually tend to get slowed down by the other gas molecules in the container, because they'll be attracted to it to some extent. So you expect sort of the pressure to maybe be decreased a little bit. So one way you can do that is you can say, all right, let's take P, and this time we're going to take P and we're going to allow the sign to be whatever we want. But what we're going to do is we're going to say P plus A over. Now what we're going to do is take the volume per mole and square it, because it turns out it's inversely proportional to or is proportional to the square of the density. Okay, so the density would be N per V. So I'll put it in the bottom. That made it V per N. Now you see the positives there, but what we're trying to do here is we're trying to account for that part of the pressure that is taken away. And in fact, you could look up experimentally to find out what A is for any particular gas. And you just look in the temperature range that you're at. And you can then say, this is going to be this P times V minus NB is equal to nRT. And this is a version. This is a version of van der Waals equation. And I think it's WAALS. Now, did some mixed gas diving. Well, actually, did some research into mixed gas diving as well because I was going to get my certification. So I read the book, but it turns out that's one area where you actually do use van der Waals as opposed to the ideal gas law, because you're filling up a scuba tank and you really need to be a little bit more precise when you're putting in oxygen at a higher percentage, because that's what like nitrox is. So oxygen in the air is about 20%. But if you go deep enough, oxygen actually is toxic. So there's a partial pressure of oxygen at which you start having seizures, breathing the very thing that you need. Okay. So you can actually make your diving experience a little safer and a little more enjoyable by increasing the oxygen level. And there's a nitrox 1 and there's a nitrox 2, and nitrox 1 is a higher amount, but then nitrox 2 is a slightly lesser amount of oxygen, but still more than you have in the atmosphere. So you could imagine, for instance, what if they turn the oxygen percentage up to 40% instead of 20? The nitrogen is what gives you nitrogen narcosis, which means basically nitrogen drunkenness. So one of the things that happens at depth, and I've seen it even at 80 feet and 100 feet, is you get a little disoriented scuba diving and you make bad decisions just because you're drunk. Nitrogen literally acts like alcohol at that depth. So if you cut down the amount of nitrogen and increase the amount of oxygen, long as you don't go too deep, that's good. You're safe and you're less likely to make bad decisions and stuff like that. But if you really want to be a deep water diver, you go like to the grotto, the Blue Grotto in Florida. That's like 260 foot deep, just hole in the ground. I think it's 260, might be 280, something like that. And they actually will train you to go to those depths, teach you how to use your tables, teach you how to fill your own tanks with various things. They'll use not only nitrox, which if you go too deep, you don't want to use nitrox at all because oxygen becomes dangerous. You might even cut back on your oxygen, but you can replace the nitrogen with helium, for instance, and then you use heliox, or you can use trimix, which would be helium, nitrogen, and oxygen. The helium is really good because that has no narcotic effects whatsoever, but it comes out of your blood system way more slowly than nitrogen does. So you have to spend about 3 or 4 times as much time and ascending just to keep from getting bent, basically. So those are some alternate things you can do. But it turns out when you actually go to work out how much oxygen to put in and how much air to put in, you can't just rely on the ideal gas law. They actually use the van der Waals equation for that. So I think that's a sort of an interesting little tidbit of reality and where it's used. So any questions on that? Now, your book does go on. It talks about actually some really good, science facts. Like, there's a critical point at which if you're below the temperature, the critical point, say for water, then water doesn't have to be in a gaseous state just because it's 100 degrees Celsius. For instance, if you put water in a scuba tank and then you filled the rest of it up with air and you did the scuba tank, warm that up safely. Now, this is not an experiment I'm suggesting you do, because when you do warm up scuba tanks, there's a real danger of that. But if you warmed it up, say, what you might find is because the scuba tank has a much higher pressure than atmospheric pressure, you might be able to find that the water is still liquid even at 200 degrees Celsius. Okay. It turns out the critical point for water, and that's the point at which it can only exist as a gas, is 317 Celsius. So once you get above that, there's no amount of pressure that's going to keep that in the liquid state. And the amount of pressure that you need is like 280 atmospheres or something. Actually, I think maybe it was 280 or some pascals, but your book has a table on it. So that's kind of interesting stuff. Your book also mentions, for instance, the dew point, humidity, that sort of stuff. And typical stuff that you learn sort of in earth science, but now you have the math and the skills to make sense of it. So like if you want to know the relative humidity, you take the partial pressure of water that you have at that time and you divide it by the saturation pressure of water, and that'll actually, for that given temperature, and that'll give you the relative humidity. So that's some of the calculations you do, and these are worthwhile things, but they're really pretty straightforward. So now that I've gotten that done and warned you to make sure you read that material, what I want to do is show you a neat little thing we can do with the ideal gas law. It's sort of, in principle, you could use the same technique to derive the ideal gas law, but in this case, we're actually going to use the ideal gas law, and that'll get us another thing to consider. So let's imagine a coordinate system. So this is your y-axis, and this is your x-axis, and this will be your z-axis out this way. Okay. What I'm going to do is I'm going to make a box about like this. And what I'm going to make is a box that has a length of L, or a width of L. This dimension right here is L. And this face has an area A, and this face has an area A. And what I'm going to do is I'm going to consider a molecule or an atom in here. We're going to pretend like these are basically just small billiard balls. That's sort of what happens, or that's sort of what you have to do to get the ideal gas law, is you pretend the molecules are really hard, small objects that only interact with each other through collisions, and that happens really quickly, and kinetic energy is always conserved. So they're all elastic collisions, and the collision happens so rapidly that the forces of attraction between the atoms can't play any role in it. So that's what makes it an ideal gas. Now, if I take and put in there a molecule or an atom of mass m moving with a velocity v, if I zoom in on that, what I'd see is here's the wall. Now I'm switching to one dimension, say, and here's my atom. And what my atom has is a velocity component in the x direction, a velocity component in the y direction, or excuse me, in the z direction, and then a velocity component in the z direction, or excuse me, y direction this time. And that is the total velocity v. So v is actually equal to vx I hat plus vy j hat plus vz k hat. But I'm just going to pay attention to the x component right now, because what's going to happen is this ball, which is an atom, is going to hit that wall and then fly back off. And because its kinetic energy is conserved, it's elastic collision, this ball is going to, in fact, leave with the same mass and the same velocity. Well, actually, sort of the same velocity. It'll be the same magnitude of velocity, but in the opposite direction, according to the x-axis. The y-axis is going to, the v velocity in the y direction isn't going to change. The z direction of the velocity is not going to change, but the vx is just going to reverse itself. Okay. Now, if you think about a gas in a container, it's the molecules or atoms of the gas banging against the sides of the container that makes the pressure. And that's what we're trying to calculate, is the pressure. So first off, I know that Newton's second law is F, the total force. In this case, we're just talking about one force acting on the wall, and it's going to be the force of an atom. That's equal to delta P over delta T. And we know that delta P is really the change in mass times velocity, right? So according to our own diagram, we have a final velocity of m times vx, and then minus the initial velocity, which is negative m times vx. So you end up getting 2m vx is the change in momentum, okay? Now, if you want to figure out how much time is between collisions, for instance, what you see is this molecule is never going to change its x component of velocity. It's going to bounce off the left wall and go from a negative component of x velocity to a positive component of x velocity, the same amount. And it might go up and hit the ceiling, but that's only going to change the y component. And it might hit the back wall, but that's only going to change the z component. So the x component is going to stay the same until it gets over to the other side, and it'll hit the wall, and it'll go from a positive x component to a negative x component that's equal in magnitude as well. So really what you want to think about is the time between collisions really is the time required for a ball to go from the left side to the right side and then back to the left side. Well, we know velocity is equal to distance divided by time. So time is actually distance divided by velocity. So what I'm going to do is I'm going to say delta T is actually equal to 2L over Vx. So that one molecule is going to hit basically every 2L over Vx seconds. So I can now say the force is equal to 2mVx over 2lVx, which is going to be mVx squared over L. Okay. Now, in reality, what we do is we can calculate Vx average, or Vx squared average like this. So we take Vx1, that's the x component of the velocity of atom 1 squared, plus the x component of atom 2's velocity squared, take the average of that, plus dot, dot, dot on up to plus Vxn squared bar. And that's just going to be equal to all that divided by n. Okay. So what that tells us is Vx squared is actually just equal to n times, or the total force is just equal to n times that. So I'm going to get now that F is equal to n times m Vx bar squared over L. Okay. Now that's the actual pressure due to all n molecules or atoms. But here's a neat new thing that we can do. We don't generally want to just talk about the x component because the pressure is going to be applied in every direction, and we're not going to be able to pick out the x component of each individual atom's velocity, though we don't need to. That's sort of the nature of kinetic theory and statistical mechanics and statistical thermodynamics is you're just treating it like a large number of things and they're going to behave like an average thing does. Well, it turns out that the total velocity squared, and I'm meaning linear velocity, so I'm not taking into account the molecule spinning or vibrating or that sort of stuff. I'm just talking about the molecule slash atom, pretending like it's an infinitely small ball moving in the x, y, and z direction with a velocity squared average given by Vx bar squared plus Vy bar squared plus Vz bar squared. Does that make sense to everybody? That's what the average of the square of the velocity is. It's the average of the squares of the components' velocities. Now, there's something called the equipotential theorem, and the equipotential theorem, that's EQIPARTITION. The equipotential theorem says, hey, if you've got a really big number of objects, on the order of millions, or in this case, on the order of 10 to the 23, like Avogadro's number, okay? And you have three ways that energy can be distributed. The law of the equipotential theorem, which is sort of the law of big numbers, says that each way it can take that energy, which is 3, is going to get an equal amount. So from that, we can reach the conclusion that Vx squared is actually equal to Vy bar squared, and that's actually equal to Vz bar squared. So you can say that V bar squared is actually equal to 3Vx bar squared. You get that? So now I can say F is equal to, I can replace the Vx squared with V squared over 3. So now I'm going to say N times M V bar squared over 3L is what the force is. Now, as I said, I really want the pressure. And the pressure is the force divided by the area. So if I take this force that I got here, that's N times M V bar squared over 3AL, what's A times L?
Volume.
It's the volume, right? So yeah, now we've got a new version. We have P times V is equal to 1/3 M V bar squared times N. But remember, we also had found that PV equals N times KB T, right? So if we really wanted to, we could turn this MV squared into 1/2 MV bar squared, and that would be the average kinetic energy. But in order to do so, I have to multiply by 1/2, but I can't just randomly multiply by 1/2. That means I have to multiply by 2 as well. So now what I'm going to say is PV is equal to, in this case, we're going to say 2/3 of 1/2 MV bar squared times N. And then we're going to say, well, that's also equal to N times KB T. And that's going to give us that the average kinetic energy is in fact 3/2 times KB T. That's the result we were going for. And what this proves is that the actual temperature is proportional in Kelvin. The actual temperature is proportional to the Boltzmann's constant and the average kinetic energy of the atoms or molecules making up the gas. Now, this is specifically the linear velocity. Again, an atom or a molecule might be spinning. It might be rotating about 2 different axes. It might be vibrating. All that motion is other types of kinetic energy, of course, and even potential energy in the case of vibration, but they're not counted into temperature. The temperature is just measuring how rapidly Vx, Vy, Vz on average the molecules are moving. So as an example, let's find out how fast are oxygen and water, or excuse me, oxygen and nitrogen gas at 20 degrees Celsius. So here's our question. How fast VRMS are, N2 and O2 at 20 degrees Celsius. Okay. What we have here is that the average kinetic energy, which is 1/2 M V bar squared, that is actually equal to 3/2 KB T. So I can say VRMS, which literally means take the square root of the square of the mean, like that. And of course, you can see when I have the equation written up here, this, when I have the equation up here, this 2 and this 2 are going to cancel each other out. And I'm going to get, dang it, I'm going to get the square root of 3 KBT over M. Okay. Now, M's got to be the actual mass of the molecule, in this case, N2 and O2. So now I can say, first off, VRMS of N2 will be equal to, and I'm using the periodic table, I just happen to know these numbers off the top of my head. So it's the square root of 3 times 1.3806 times 10 to the negative 23rd joules per Kelvin times 293.15 Kelvin. All that's going to be divided by the mass, which in the case of nitrogen is about 28.0 U. And of course, 1.6605 times 10 to the negative 27th is the number of kilograms per U. So that gets it all to the right units. And when I do this, I think this comes out to be like 480 or something. So let's give it a try. 3 times 1.3806 e to the negative 23 times 293.15 divided by parentheses 28 times 1.6605 e to the negative 27 close parentheses. That gives me the square root of, whoa, something bad happened here. Oh yeah, it left a 10 to the negative 46. I actually put a positive 23 because I missed the negative button. Okay, I'll just do it all over again. I tried to fix it and it gave me an error. Stupid thing. 3 times 1.3806 e to the negative 23 times 293.15 divided by parentheses 28 times 1.6605 e to the negative 27 close parentheses. I do have two negatives this time. This gives me the square root of 261145. And if you look at the units, you can see that they're meters squared per second squared. So when I take the square root of this, I get, oh, I was remembering the wrong one. I get 511 meters per second. Now the VRMS, you can see the only difference is going to be for the O2, it's going to be the square root of 28 over 32 times VRMS for N2. Does everybody see why that's the case? Anybody not understand why that's the case? Okay, it looks like you are getting it. So yeah, this gives me 478. That was the one I was remembering, 478 meters per second. So notice the heavier molecule goes slower. That's sort of the point, right? The kinetic energies is what balances out, because if it's a mixture or if it's a compound or something like that, with other things in it, basically if some group of atoms or molecules or whatever you're dealing with has a higher kinetic energy because they're heavier, then they're going to keep on colliding with things and getting slowed down until all the things are going the same, with the same kinetic energy, right? So yeah, if you had oxygen having a different amount of kinetic energy than nitrogen, then they would equilibrate by doing that. Whereas if you just had different speeds, that's perfectly fine because a high mass one should be going very slow to match a low mass one. Okay, so that's how that works. Any questions there? Now, when we learn about the ideal gas law, it turns out we can calculate the internal energy of an ideal gas. And it's going to be basically internal energy. We can call it E, or we can call it U, or we can call it delta E or delta U or whatever. But the main thing is for an ideal gas, it's going to turn out to be just like this kinetic energy. But when you take into account the total internal energy, you need to include, let me stop looking at this for a second and you guys look at me. So if you imagine, for instance, hydrogen, let's say water. So water is like oxygen, hydrogen, hydrogen. And you sort of think of the number of ways that something can have a energy that goes like some variable squared. That's all what we call the degrees of freedom. So if you have a molecule like water, like that, water can move up, down, left, right, and out. So that's the stuff that associates with temperature. So any of this whole molecule going in the X direction, the Y direction, or the Z direction, or whatever, those three are just what affects the temperature. So if those speeds change, that means the temperature goes up or goes down. But what can also happen is this water molecule can spin about this axis, which goes from this oxygen through this hydrogen. Okay, that is a kinetic energy given by 1/2 I omega squared, where I is the moment of inertia of the molecule, which is basically an oxygen atom, a hydrogen atom, and then another hydrogen atom over here. So it can spin about that way. So that's one other degree of freedom. It can also spin about this axis. So that's another degree of freedom. So we're up to 5 degrees of freedom so far. But this hydrogen can also oscillate in and out. That's 1/2 kx squared. So that's another degree of freedom. So we're up to 6. And this can do this way. So that's another degree of freedom. So we're up to 7. And in principle, you might even say, well, what about this atom rotating about, say, an axis right through the middle of this? Well, that would be another I omega squared, stuff like that. So all of those different ways that you can do it are different, what we call degrees of freedom. And because of the equipartition theorem, the equipartition theorem says that 1/2 kBT goes to each of those different modes, each of those degrees of freedom. That's why we got 3/2 for the kinetic energy being equal to 3/2 kBT, because that's the Vx, the Vy, and the Vz. That's 3 of them. So 3 times 1/2 gives you 3/2. So we get 3/2 kBT. And that's the expression that gives us the actual temperature. So 3/2 kBT is the average translational kinetic energy of the molecules. But if you have 7 degrees of freedom, the total internal energy would be 7/2 kBT. If you had 12 degrees of freedom, it'd be 12/2 kBT. And each one would get 1/12. So that's the bigger idea of what's going on here. And that's also why water has such a high specific heat. Water actually is a wonderful insulator. That's, for instance, why Great Britain, which is pretty much the same latitude as Canada, or a good part of Canada, they're not cold like Canada because they're surrounded by ocean. It's a little island, right? So Great Britain is experiencing all the insulational properties of water, because the water all around it can actually add heat to the air above it, and that actually keeps the air from getting too terribly cold. It still has cold winters, of course, but so do we. Even in Miami, I was in Daytona one time and it got down to like 48. So that stuff happens. But yeah, that's why water's a good conductor, or excuse me, a good insulator, because the specific heat is so high, because it's got all those different degrees of freedom that are going to steal an equal part of the energy. So only 3 go to heating it up, changing its temperature, but all the other degrees of freedom go into just increasing the internal energy as opposed to increasing the temperature. Does that make sense to everyone? All right, we'll move on then. We've got about 6 minutes left. And what I wanted to show you now is when we do this, these type of calorimetry experiments and problems, what you can find out is that if you make a plot, say, of energy inserted plus versus temperature, or temperature versus energy input. So let's say our axis looks like this, and our other axis looks like this. And this is in fact Q, that's the amount of heat put in. And this is in fact T in say degrees Celsius. Okay. You can actually look up these values, but basically if this number down here is negative, let's do a little smaller than that. Let's say negative 20. No, negative 10 would be close enough. Okay. What's going to happen is from here to here, there's going to be a straight line. So as you put heat in, more and more heat, you're just warming the water, which is ice at that temperature, of course. But then once you reach 0 degrees Celsius, basically you just keep adding energy until it can change state. So you're basically adding heat to the actual ice to break up the bonds of the lattice. Okay. This, at least when you're going this way, is called the latent heat of fusion. Okay. Once you put in enough heat to raise the temperature to 0, then you've got to add an additional amount of heat equal to the latent heat of fusion in magnitude. And that's enough to break the bonds. And then it's going to start off again. Let's say this is 100 degrees Celsius. It's going to start off again, having yet another straight line, but not necessarily the same slope as the last one. And then all of a sudden, it's going to reach equilibrium at 100 degrees Celsius. And it's going to basically stay at that temperature, assuming we're in the right pressure range, until you add enough energy to break the the intramolecular forces or the atomic forces, the forces of attraction between adjacent atoms in the liquid. They're still held to each other, though the one atom can roll across another one and then stick to the next one, or it can maybe go across 3 or 4 and then stick to that one a little bit. There's still a force that's holding it there. And in order to break that, you have to apply a latent heat of vaporization. So they call this one like LF, and they call this one like LV. Okay. Once you add enough of that heat, and I'm not drawing this to scale necessarily, then it can go ahead and go up at a different slope. And you keep, now that it's in the gaseous state, you can keep adding heat to it over and over and over again. It's just going to keep raising the temperature. Okay. So that tells us really there's two modes by which you can put energy into a system. One of them is Q added. If I add an amount of heat Q to M mass of a substance that has a specific heat C, then that's going to cause a change in temperature delta T. And remember, delta T is generally T final minus T initial. Okay, I'm going to say a caveat about that. So, okay. Now, the other thing you can do is Q can come in and just be applied to a mass M, just to make it not change temperature, but change state. And that would be times L. That could be LF, that could be LV, that could be LS, which is what carbon dioxide often does. Can anybody think of what that LS is for?
Sublimation.
Yeah, there you go. Because dry ice is what carbon dioxide is. And of course, it sublimates. It goes straight from the solid to the gaseous state. So you could use one of those as well. So the reason why I said about this caveat is a lot of books will say the total change in heat or the total heat added is equal to 0. And then you got to be very meticulous about keeping your signs straight, which means you always want to use T final minus T initial. I don't like doing that. What I say is Q gained is equal to Q loss in calorimetry. And what I mean by that is, let's say we take a flask and fill it up with water and heat it up. Okay. And we lay a little block of, say, aluminum in there, or let's say a block of steel. And we bring this temperature from T equals 20.0 degrees Celsius to T final equals 100 degrees Celsius. Okay. And we leave it there long enough that we know, since the metal is a conductor, it's going to reach equilibrium with the water, right? And then we take a cup, maybe the cup's made of aluminum, okay, and it's actually on a little wafer thing that stops conduction of heat from the cup out to the outer liner, which is another container. Actually, it should go right here. So you can make sort of like a double-walled thermos, if you will. And by it being held up by that little, let's say, cardboard or wooden ring there, then only that thin sheet of cardboard or wooden ring can transmit any heat from conduction through the aluminum cup to the outside. So you basically made a pretty good thermos where none of the heat should escape. And you could even put a lid on it, say, whoa, I don't know what happened there. You could even put a lid on it, say, and put a little thermometer in there and fill this up with water. Now you're going to take this metal out and put it in here. The metal, the iron, will be T initial equals 100.0 degrees Celsius, whereas the H2O, which might be, say, 50 grams, and the aluminum cup, which might be 20.0 grams, their initial temperature is 20 degrees Celsius. Okay. So if you had that problem, I would say the thing that's gaining heat is the water and the aluminum cup. So from this equation right here, that would mean this is aluminum cup and water. And then I make sure everything's positive. So I don't do T final minus T initial. I just do T big minus T small. Okay. And then this side, the only thing that's really losing heat is the iron block. Okay. So the iron block, of course, isn't going to change state. Neither is the water, neither is the aluminum cup. So on the left-hand side, you're going to have M, the mass of the cup, times C of the cup, in other words, specific heat of aluminum, times T final minus T initial, because you know the water is going to warm up and you need it to be positive. So you're going to do T final minus T initial for the aluminum cup. And then you're going to do M, the mass of the water, times C, the specific heat of the water, times T final minus T initial, which is the 20 degrees Celsius. Again, so it'll come out positive. That happens to be consistent with the definition of delta. But on the other side, you're just going to have the block. Let's say the iron block, which weighs, let's say, 23.0 grams. You're going to take that iron block, multiply that mass times its specific heat, which you can look up, and then that's going to be multiplied by T initial, or excuse me, T initial, which is 100 degrees Celsius, minus T final, because again, we want it to be positive. So with that in mind, your equation would be, let's say, I think I said 50.0 grams for the water times 1.00 calories per gram Celsius degree times T final minus 20.0 degrees Celsius plus, what did I say the aluminum mass was? 20 grams. So 20.0 grams times specific heat of aluminum. I don't remember that, but I'll just write C aluminum from table. Crap, we went over again. All right, everybody's free to go, but I'm just writing this out. It's C aluminum times T final minus 20.0 degrees Celsius. That's equal to the other side, which I think was the mass of aluminum was 23 grams. Or excuse me, iron was 23.0 grams times C iron times, in this case, it'd be 100.0 degrees Celsius minus T initial, or excuse me, T final. And that would allow you to actually solve for T final. So that's a very typical problem. I just wanted to give you an example. Y'all can solve that if you want. You can look all this up and do it for an extra credit if you like. So everybody's free to go. I'm sorry I ran over. I thought I was almost about the time to run over, but I actually had already exceeded it by 4 minutes. So have a good one. I'll wait for the last person to leave in case anybody has any questions. Any questions? Arnold, do you have any questions, sir? I don't believe you're here.